I am unmuted. Speakers are not muted. The chat window is open. The recording has started, so we're good. Welcome to Monday. Next week is reading week. I never looked forward to reading week more than this year. It's not you guys, it's just I'm tired. Just frees up a little bit of time. Reminder, there is going to be an assignment due, or I guess not due, but done on Friday and Saturday of this week. And then you're free. Then you're into reading week. If you don't want to do it on Saturday because it's reading week, then do it on Friday. And that's fair. Okay, so I'm going to start today's lecture by taking up a question I got in an email. I'm just going to share my screen. I'm going to share a different screen, I guess. So we had this question here, which is, which of these molecules is not a resonance form of this? And the question I got was, how did I get so the answer was this one down here. The reason this one is not a resonance form is suddenly this carbon picked up an extra hydrogen, and yeah, you can't do that. And this carbon lost a hydrogen, and you can't do that either, because then it's not resonance because you're moving atoms around and everything's bad. But the question I got is, how did you get A, you being, I guess, the scientific community, from this? So I am sharing this on my laptop and not my tablet, and so I can't draw this. But let's, for example, you can take this double bond here, this benzene ring, and you draw an arrow where you put both of the electrons onto this carbon. That's going to make this carbon negative, like this. It's going to make this carbon this one here positive because it's going to be short of the electrons. That positive and that negative are both going to be in p orbitals. So the lone pair here is going to be in a lone pair in a p orbital, and this is going to be an empty p orbital that's positively charged. Then these electrons in a p orbital next to a positively charged p orbital can make a new double bond. So they're going to draw an arrow going towards the space between those two carbons, and that's going to generate this double bond. So that's how we can generate A from this guy here. So we break this double bond onto this carbon, and then we push these guys over here to reform the new double bond. Okay. I'm going to have to now switch over to this one. Okay. From current slide. Which topics will be on the assignment? I think to what we get done on Wednesday is going to be what's on the assignment. So what the hell have we been talking about? I guess we've been drawing some arrows. We've been talking about some resonance structures, acid-base equilibria. We've talked a little about Newman projections, and today we are going to talk about rings. Probably, if we get done the ring stuff, I'm not going to start. There won't be any stereochemistry on the assignment. We won't do any RRS stuff on the assignment because that's going to be maybe just a little bit too tight. So, if you Divjaw says the assignment going to have similar format to the first one. Probably. Again, you assume we've written the questions. We have not yet written the questions, but I think it's going to be similar format to the first one. And will the topics from the first assignment also be on the second assignment? We're not going to specifically evaluate the topics from the first assignment on the second assignment, but everything that was on the first assignment goes into the second assignment. So in the first assignment, we were talking about, hey, which of these is a valid resonance structure? Well, if you need to evaluate charge stability, you need to be able to draw your relative, your proper resonance structures. You need to be able to think about the Lewis dot diagrams and the Lewis angle diagrams. You need to be able to think about formal charges and all that stuff. So, and hybridization. So, although we're not going to be testing the same stuff, it's all, we're scaffolding. Like all that stuff is now implicit knowledge that you're supposed to have to be able to do the next series of questions. Sorry, I think I heard somebody laugh on this. So if somebody's not muted, just check your microphone if you're not. So That was a completely appropriate response, though, so it's all good. What I want to do today is I want to talk about rings. Unless there's any other questions. So somebody actually already asked questions about rings, but if there's any other questions anyone else has, we can cover that aren't about the assignment. Anything anyone had particular difficulty with in Lecture 9, Conformations of Simple Rings and Systems? Okay, we'll just get started and we'll see what comes up. Feel free to interrupt. So let's say we have a disubstituted cyclohexane like this guy. The question could be, provide the most stable chair conformation. Distinguishing between cis and trans and ring drawings. Yeah, we can do that. Okay. So let's say we have this. Hopefully we'll be able to determine that this is a trans dimethyl group. So trans is always relative. A single thing is not just trans. Like I can't say this methyl group is trans. That means nothing. I can say that this methyl group is trans to that methyl group. Trans is a relative measurement. It's a relative analysis. So what I can say is this is a trans dimethyl cyclohexane because there's only 2 of them, so I must be talking about the 2 substituents. If there were 3 substituents, I couldn't call it either a cis or a trans cyclohexane. We'll do an example like that. I could talk about individual substituents being cis or trans to each other, but there's no way to talk about the system as a whole if there's 3 things. Yeah, so we're going to do axial equatorial drawing right now. Yeah, chiral and achiral stuff is next lecture. So if you're on that, you're done well, Amanda, and you're a little bit ahead. I'm just going to double check my. Oh shit! What? Oh no, I'm sharing the right screen. Why is it saying I'm sharing this screen? I don't know. Okay, it's all good. I'm just getting very confused. I'm just double checking the schedule. I'm pretty sure that we're supposed to be talking about rings today. Excel's going to take forever to load up. Actually, we're talking about rings for the next 2 days. And if we're ahead, we can always talk. If nobody has any more questions about rings and everyone's really happy with drawing rings, then we can move on and spend a little bit more time on stereochemistry or talk more about resonance or something else. It's the flexibility of the system. Anyways, we got 2 classes to talk about rings. We might be able to fill them. So trans is relative, always relative. And it means across, transatlantic. Yeah, so we have these 2 methyl groups and one is up, one is down. So one has the dark wedges, that means coming out of the page towards me. One has those dotted lines, meaning going back into the page away from me. And the question is, provide the most stable chair conformation. Well, that's not a chair. So if you remember, I have a little tutorial in there on how to draw chairs. I'm going to try and follow my own tutorial's advice. I no longer draw them this way, like using this set of lines. So I'm drawing 2 sets of parallel lines and then closing with the 3rd. It's not bad. So again, 3 sets of parallel lines. You know what? I got multicolored pens. I don't know why I'm not using them. Three sets of parallel lines. Now, when you're first doing this, what I strongly recommend you do, literally number your atoms. Doesn't matter where your numbering starts here. Just if the numbers above are going clockwise, these numbers below better be going clockwise, because it's going to matter when we're starting. Just get into the habit. It doesn't matter yet, but in 2 lectures when we start talking about stereochemistry, it's going to matter a lot. So I strongly recommend that you get into the habit of, if these go clockwise, these go clockwise. Just when you're starting, do this. Later on, you can do this in your head. Great, awesome, good for you. Okay. Now, on each of these vertices, each of these carbons, there is one. I'm going to actually draw it over here. Very, very big. The reason we draw at this angle is because the tetrahedron, it's always completely appropriate to draw one substituent absolutely vertical. And it's still a proper tetrahedron. So there's a vertical substituent, and note that they switch. And kind of the point, if you think of the bonds coming together as an arrow, I think there's something I can do to make my screen bigger for the recording, but I'm not going to do anything too fancy here. But you know, if you think of the vertex, like of this carbon back here, this one right here, you can see those two bonds come together as an arrow. They point up. The vertical should be up, and that's what we have. And if you try and sort of do that arrow thing for any of the other ones, it points towards which way the axial or the vertical substituent. These are your axial substituents because they are parallel with the vertical axis, or they are axial to the plane that is formed by the ring. It's not really a plane, but it's kind of a plane. That then leaves an equatorial substituent on each of them. So how do you figure out where the equatorial substituent, how to draw it? Well, there's 3 sets of parallel lines. The set of parallel lines that doesn't connect with that point is the one that the equatorial substituent should be parallel to. So if I look at this point, it's parallel to this set of lines. This is the one that it doesn't connect with that carbon. Similarly, that one's also going to be parallel. Note that we now have a nice tetrahedron. Similarly, take that set of purple parallel lines, this one and this one should be parallel to that. And then the ones I'd like drawing the least. I just don't like drawing these ones. Mostly because I can never get the angle right on the back. And if it's hard, just makes it a bit more unpleasant to draw. So we have 3 sets of parallel lines. The axials are vertical, like vertical. That's why we draw this thing kind of at a slight angle, so the axials are vertical. Always draw your chairs with the axials vertical. If your axials aren't vertical, you make our lives really difficult trying to figure out if you're trying to draw something axial or equatorial. And if we can't figure it out, we're not giving you the benefit of the doubt. So save yourself and just draw your things axial. You're not going to trick us because we're mean. Well, actually, the GAs are mean. I normally go back and I give you, sometimes go back and I check and go, hey, it is actually kind of axial. It's kind of clear, but they put up with a lot in their normal lives, like having to work with people like me. And so they really don't have as much patience as they could have. And after staring at a few hundred of these things poorly drawn, they kind of lose their freaking minds. So be nice to the GAs. Anyways, so this is how you should draw them. All your axials should be vertical. All your equatorials should be parallel to the set of lines that are not in contact with that vertex. And it makes a lot more sense drawing in colors than it does saying that, because it's just words otherwise. Now, if we go back to the example we have here, I arbitrarily wrote a carbon 1 as back 1. You could have put carbon 1 anywhere along there that you wanted. It would have been fine. Yes. Everything not in blue So that's red, purple, that's in, you know, we can underline this. Green, red, and purple. Well, right now we haven't figured out what to make axial and what to make equatorial, Melitza. So I've just drawn, those are the equatorial and axial positions. Often there's going to be a hydrogen at all of those. Like if it's just cyclohexane, everything there is a hydrogen. But in this case, we're going to look at that. So carbon 1 is coming out of the plane towards me. And if I look at that back carbon, it's this one here. There are two substituents. There's an axial and an equatorial. The equatorial is above the axial. The axial is pointing down. The equatorial, therefore, it's not completely clear, must be pointing up because it's not pointing down. This is pointing up. That means that there is an equatorial CH3 group there. Carbon 3 is pointing down at this carbon. There's an equatorial on that because every carbon has an equatorial and an axial. But the axial is pointing down, the equatorial is pointing, therefore pointing up. The equatorial always is the opposite of the axial. So yeah, it's really clear if the axial is up or down. The equatorial is the other thing. So we can draw that. That's one of our chair conformations. Every chair can be flipped. And I am not, I'm going to try. If you have a model kit, make a 6-membered ring. Actually, for today's class and next class, you should probably just make a 6-membered ring. So if you have a model kit, that's great. Let's see if I can figure out a way to. What if I stop sharing for a second? That doesn't help. Oh, that didn't help either. You just get a humongous picture of my face. Yeah, maybe. Okay, so you've got a 6-membered ring. I have no idea what you see. You don't see anything. Aurora said, what are the chances of moving the assignment to after reading week? Well, you have a midterm like the week after reading week. I don't care. Sam and I will actually breathe a sigh of relief. I prefer to do it after reading week, but I know you guys have lots and lots of midterms. Okay, you see me. Okay, that's terrifying. There we go. So we have a 6-membered ring. If you can see, they're trans. So we have an axial and equatorial. And what you can do to try and get this right is you should be able to see that we have a plane made by 4 of the carbons. They kind of form a square right here. And then one's sort of flat and one's kind of coming up. And our axial is coming straight up, and our equatorial is going out at an angle. Again, strongly recommend you go through this exercise at home, build a model kit. To flip the chair, what I'm going to do is I'm going to go to the boat conformation. Notice it's a boat now. There's still this plane, but now it's flat. Now I've got this whole boat thingy going. And so I bring one side down, I bring the other side up. So whereas I started with this carbon above and this carbon below, I now move this carbon below and this carbon above. And it didn't matter which way it was. This is the same, it's symmetrical in all 6 of them, which is a little hard to tell if you don't have a model kit. Please go get a model kit. And what I've just done by flipping the chair is I've turned all my axials have become equatorial, and all my equatorials became axial. So keep an eye on this axial, keep an eye on this equatorial. As they flip, they've switched. The equatorials become axial, the axials become equatorial. Okay, you know what? If it's not unanimous, we have to follow the syllabus. So syllabus says this week is this week. Again, you've got 48 hours. It's going to be just to build on this material. If you're in this live chat following along, because right now there are 84 of you in this live chat. There are, 340 students registered in this course. You guys are fine. You will be fine. That's why just don't rush it. Think about them. You've got 48 hours to think about the question. And we'll tell you how many questions there are again. Yeah, I will. Okay, I guess I'm showing my boat. So again, in a chair, you know you're looking at a chair when you have a plane and you've got one carbon below, one carbon above the plane. A boat is when both carbons that aren't in a plane are on the same side. They're both above or below. And we can see why boats suck. You know what? I'm gonna do it a different boat. I'm gonna exaggerate why boats suck. Okay. So I've made a slightly different molecule. Here's a chair. You want to keep an eye on it. Everything's equatorial. I've changed my thing, so now I have everything equatorial. And if I go to the boat, the sucky boat, there's a bunch of different boats that are possible because there are like 4 are in the plane. I'm just going to make sure I get the right sucky boat. There we go. This is a really sucky boat. You can see why. So in here, I've got a plane and I've got 2 carbons below. So both these are on the same side, not one below, one above. They're both below. That makes it a boat. It kind of looks like a boat if you have a really, really vague idea of what a boat looks like. But boats suck because look at this. These guys are basically whacking into each other. These are banging into each other. You can actually hear the clicking. That's not good. Things should not, they shouldn't even be close enough to be able to click, let alone actually click. So boats are awful. Chairs are when we have the plane, one above, one below. Yeah, I will draw it on paper again, and I'm going to switch back to drawing on paper. Share my screen. So let's just worry about the chair first, then we're going to worry about the boat. So here's one chair, but I said provide the most stable chair conformation, and you can't do that if you've only drawn one chair. So you have to draw the other chair. So this is my how to cheat at drawing chairs. So there's a bunch of ways you can do this. Some people would say you have to insist on flipping it. You don't need to. All you need to do is move every atom 1 over clockwise or counterclockwise. So if 1 was there, now 1's here, 2, 3, 4, 5, 6. I actually really suck at drawing chairs with the other slant. You'll find me always drawing them this way. So carbon 1 is above. At this point, that's axial. Carbon 3 is below. At this point, that's equatorial. All I've done is I've flipped the chair and changed my viewpoint a little bit. All my axials become equatorial. All my equatorials become axial. My ups are still up. My downs are still down. I am still going clockwise or counterclockwise in the same order as I went with. So I'm still going clockwise with my numbering. All my ups are still up. All my downs are still down, but my axials and equatorials have flipped. That means I have flipped the chair. This works every time. Okay. So can I re-explain this? Okay, so we agree that these are trans to each other. Carbon 1 methyl group is coming out of the plane. The carbon 3 methyl group is going into the plane. I'm going to interact directly with Madison on this. So Madison, you're my interlocutor here. Okay, so we have arbitrarily started with the chair on the left. and we have arbitrarily numbered it this way. You could have numbered it any other way you wanted. Since we're going to draw both chairs, it doesn't matter which one you do. Okay, so let's say I arbitrarily number this as carbon 1. Now what I'm doing is I've gone from looking from directly above the chair, which is kind of what I'm doing here. I'm looking directly above the ring, God's eye view, to, you know, late 1990s, early 2000s RPG game isometric view, where I'm like, you know, 45 degrees from the action. I'm not looking directly above. I'm not looking directly in the plane. I'm kind of looking at an angle. So if I'm looking at carbon 1, and I said this is carbon 1, I know that the methyl group in carbon 1 is coming out towards me. And I know that that carbon is this carbon, and there are 2 locations for substituents. Are we good there? Cool. Okay, awesome. You're gonna have to sort of sit on the yes button or the no button. Okay, because your question's really good. I know if you're having trouble with this, a lot of other people in this room are having trouble with this too. So what we can say is that it's clear that this guy here is below. It's pointing down. It's axial down. The axial is down, like it's pointing into the pit, down into hell. Whereas this equatorial is not pointing down. It's not clear it's pointing up, but it's clear it's not pointing down because the other guy's pointing down. And you're either up or down. So if the other guy's down, this has to be up. Are we good on that, Madison? No, Lauren, that's not true. But I'm going to finish this with last. Okay, good. Okay, so we can agree that then we have to draw that CH3 equatorial if I drew the chair this way, and I assigned that as 1. By definition, that CH3 must be equatorial because that is the up position at that point. So at carbon 3, 1, 2, 3 over here, and I've got to be carbon 3 because I'm numbering clockwise and clockwise. Like if that was 1, this is 3. At carbon 3, the methyl group is down. I lost Melitza. Okay, Melitza, see if we can do this time. Yeah, because if you put an equatorial on carbon 3, it would be in the up position. But that's not up, it's down. So if I had drawn this thing here is not that thing there, because we can draw, if you want, you can draw in your hydrogens just to, like at the other substituent, just to make it really clear where the hydrogens are in the up or down. And now it's clear that this methyl group is above the hydrogen, but I just said it's below. Because what's implied here is that there's a hydrogen in the other, in the 4th position. We haven't drawn it in, but it's implied that there's a hydrogen there. And so if on carbon 1, the methyl group is above the hydrogen, and on carbon 3, the methyl group is below the hydrogen. But if I draw the methyl group above the hydrogen, that's not the same thing as that. Yes, Alan. And I'm going to play with a caveat on that, but yes, you're right. That's by far the safest way to do it, and it will always be right. Did I lose you, Madison, or did this work? Over why that one's down and that one's up. Melitza said, how do we know that carbon 1 is not axial and carbon 3 is not equatorial? We don't. That's why we have another one. We drew another chair. These are both possible representations of this structure here. So we have 2 possible chairs. Just arbitrarily the way I numbered it. Oh shit, okay. Switch over to. Okay, I'm gonna put this at a weird ass angle, and I'll try and draw this before. Where's my charger? Battery on this Surface is not great. I cannot recommend a Surface Pro. Okay. It also helps if you put the charger into the charger slot and not into the SD card slot. So, okay. So there's always two chairs. There's always a chair where something is equatorial, and there's another chair where that thing is axial. Always, 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 always. There are always two chairs. No more than two chairs, just two. So here, carbon 1 is now axial. It was equatorial. It's still up, but now it's axial. Carbon 3 was down and axial. Now it is down and equatorial. That will always be the case. You will always, in your two chairs, you will flip all your axials and equatorials. So the trick question here is, Nora was saying, so would the second chair be more stable? They're the same. They are identical because they both have one equatorial and one axial methyl group. There is no difference between these two in energy. They are identical in energy. So we'll do one where it is more screwy. So coming back to Jesse and Lawrence are the same thing. I think so, Malitza. Yeah. Let's do another example. This is why we have two classes for this. This stuff is kind of tricky. Okay. No. Okay. So let's say we have this molecule. You know what? No, I'll leave it simpler for now. We'll come back to something a bit more complicated. We'll start with something simple. Relatively simple. So we've got two groups here. You know what? I'm going to make them trans because I'm going to address directly Lauren and somebody else, Jesse's question. So Jesse and Lauren both said, look, if they're trans, does that always mean one's axial, one equatorial? No, it doesn't. If they are 1,3 trans, yes. But this is a 1,2 trans. And now if we draw our chair, let's just draw our chair. There, nice chair. Arbitrarily number your atoms. I like clockwise. I think clockwise. I actually have trouble with counterclockwise and clockwise occasionally, which is really bad for an organic chemist. I also have trouble with left and right. Okay, so my one position, you know what? Take a second, try and draw it in. I'm gonna give you, a minute or something. Try and draw what you think. Just either chair. Well, no, I guess this chair. I numbered my atoms. And if you get done that chair, try and draw the other chair. And I'm going to drink coffee because I desperately need coffee. Alan, I'm not numbering this like numbering the molecule. Yeah, the OH would be carbon 1 if you're naming the molecule. I'm just numbering the atoms to keep track of atoms. But Alan, you're absolutely right. The OH would be carbon number 1 if we were naming the molecule. But we're not naming it. And we would also go counterclockwise then, right? We go 1 for the OH, 2 for the isopropyl to keep the numbers low. Yeah, you're absolutely right. But just that's, if you don't need to name it, don't make your life harder. But it would be completely correct. You'd get the same answer if you did that. It wouldn't screw up your answer at all. The numbering is completely random which way it go. As long as you're consistent within the same question. Okay, so if you try drawing this in now, hopefully you're thinking, okay, this is carbon 1. It's got an axial and an equatorial. And if it helps, draw in your hydrogens. The isopropyl group is above the hydrogen. There are 2 positions here. The axial is above the equatorial. Because the isopropyl group is above the hydrogen, it must still be above the hydrogen. That means it's axial. And carbon 2, the hydroxyl group is below the hydrogen. There's 2 positions. If it helps, draw in your positions. Just draw chairs with substituents until your mind goes numb. It's actually not a horrible use of your time. You can sit there and watch Squid Game and draw in chairs. Nice things no one dies in organic chemistry class. So we have this chair. This does not look like the more stable chair, though you can't be sure till you have drawn both chairs. If you're asked to draw the most stable chair conformation, you don't have to draw both chairs. You could just draw the more stable one, but you better do it in your mind if you don't do it on paper. And so if we draw the other chair, all I'm going to do is going to slide every atom over, 1. See, that's me drawing a bond which wasn't really axial or equatorial. And in this case, carbon 1, the isopropyl group is above the hydrogen. And on carbon 2, the hydrogen is above the hydroxyl group. Well, okay. So, no, it's not a dumb question, Madison, because it means I screwed up. Yeah, so in this case, both are axial. In this case, both are equatorial. So what we're looking at here is we're telling that this isopropyl group is coming out of the plane of the page. This hydrogen must be going back into the plane of the page, which means the isopropyl group is above and the hydrogen is below. And on this bottom one, the OH is going into the plane, the hydrogen is coming out of the plane, so the hydrogen is above the OH. So if I switch my view here, I better be seeing that the hydrogen is in the up position, and this axial position, this axial down position is the OH. And here, the isopropyl group is up, coming out of the plane, and the hydrogen is going back and down into the plane. Did that make sense to you too, Drake? And Divjot and Carolyn? Or did I lose all 3 of you? Yeah, we can draw thicker lines in chairs if you like. Do we draw thicker lines? Well, normally we draw them like this. If you look at ChemDraw, it will actually change. So if you try and draw a chair in ChemDraw, it will draw it slightly differently. It will draw it something like that. So it's kind of like a thick bar here at the front. Man, I've really fucked this up. This looks like shit. I'm gonna blame it on the stylus, but you and I both know it's because I can't draw worse shit. Okay, I'm just gonna draw the chair. And then I'll thicken the lines. So wedge coming towards us, wedge coming towards us, and then a thick bar representing that it's already really out towards us. So you'll see this occasionally using sort of wedge drawing to try and give it some 3-dimensionality. It looks really like garbage when I draw it. You might be a much better drawer than I am, so it might look better for you. But if not, you can just draw the bicycle lines like I'm going to. Yeah. No, you don't need to draw ChemDraw. You can draw it by hand. ChemDraw is not mandatory. It's amazing for writing lab reports. I spent $5,000 on a license, a perpetual license for myself, so I can draw things. So I bought a car instead. I bought software. It's a fancier version of it, but still, just as ridiculous. Okay, I didn't spend my own money. I spent my professional development funds on it. So yeah, there's only ever 2 possible chairs for a 6-membered ring. And yes. Yeah, like what I've done here is I've actually flipped the chair. Like if you get out your model kit, Ken. Stop sharing for a second so you can see my ugly face again. If you get out your model kit, so here's one chair. Keep your eye on the prize. Okay, by the prize, you know what? I'm gonna put a red. I'm gonna use a red ball. Screw it. I'm actually putting a red ball in the thingy. Do I got a blue ball? I do. Okay. And replace this with a blue one. Okay, it's not blue. It's kind of like washed out magenta, but whatever. And we'll stick a gray thingy on it. Just a little bit easier to keep track visually. Okay. The only problem with the blue one is they're meant to be extra flexible. So I've got, if we keep an eye on this, we've got 2 labeled atoms. I've labeled one in red, one in blue. This is a chair. Note that the red is equatorial, the blue is axial right now. And I'm putting the red up here. Note that also the chair is I have the thing on the left, I have the down carbon on the left, the up carbon on the right. My right, my left. Might be different for you. I can't be bothered to figure it out right now. What I'm going to do is I'm going to flip the chair. Okay, now my up carbon's on the left and my down carbon's on the right. But I don't want to draw that because I'm lazy. So I rotate the chair a little bit. And now suddenly my down carbon's on the left and my up carbon's on the right. So all I've done is I've flipped the chair and I've rotated 60 degrees. And that's what I've done with my drawings too. I flipped the chair and rotated 60 degrees. So that's why I sort of shuttled everything one atom over. But it looks exactly the same as the original chair. Like everything down, up, all the same angle. It's just every carbon is 1 carbon over now. So I flipped the chair and rotated 60 degrees. Down, up. If I flip the chair and don't rotate 60 degrees, up, down, they're wrong. So that's why you do the rotation. And then you don't need to ever draw more than one shape of the chair. You only need to master drawing one version of the chair. You don't need to actually ever draw the other one. I don't know if that helped you. If not, please get out a model kit. I can't. This is like model kit central. This one, the last class, is like the class to have your model kit. If it really helps you, go back over this lecture when you do have a model kit in front of you. Follow along, play with the model kit, pause it. Ignore me and just play with the model kit. Either of those things work. Okay. So we're back with this. So if I asked you which one of these is more stable, what would the answer be? Second one, absolutely. Okay, so the good news is you're not going to have to flip anything that's not a 6-membered ring. We're going to consider that advanced, and this is an introductory course. You're going to need to be familiar with cis and trans, though. So I got a question. Can we do something that's not a 6-membered ring, please? Yeah, let's do a 5-membered ring. Now, you can blame Deepashika for this. So if there's any hate for this, I'm just the messenger. So we have a 5-membered ring. They're trans to one another. How do you draw a 5-membered ring? Well, a 5-membered ring actually just looks like a truncated 6-membered ring. It's called the envelope conformation because it looks like an opened envelope. Like here's the envelope and there's like the tag of the envelope and it's kind of up. Now this isn't a chair. All 6 atoms are not equivalent. 4 of the atoms are now in a ring and 1 is not. And this throws off everything. So if we get out, you know, my handy model, and I'm just going to excise this poor carbon and I'm going to stop sharing so my picture gets real big. For the recording, stop sharing. This is a 5-membered ring. It's got 2 substituents on them. They're trans to each other, just like in my image. I think I have them trans. Yeah, I did. Okay, so it's a 5-membered ring. I've drawn it right now. I'm holding it so it's flat. It is not happy flat. It goes to an envelope shape. So 4 of the substituents lie in a plane. 1 goes above the plane. But what we notice is we've lost this whole axial equatorial thing. Like, I'm looking at this. This is axial. It's not axial or equatorial. They're both the same, right? They're both kind of equal with relative to the plane. So you no longer have axial equatorial. The other problem you've got is if you look straight down that bond, note that you have complete eclipsing. These bonds completely eclipse one another. So the top ones. And it's kind of a problem with 5-membered rings is on that back side, you have that complete eclipse. Now you have a more staggered view on the other carbons, but it's kind of confusing. It should be staggered. And so if I don't have it staggered here, it's because I screwed up a little bit. Yeah, they're staggered. It's not completely staggered, but it's partially staggered. So 5-membered rings suck because the angles are tough. So somebody asked in a previous class, talking about the difference between torsional strain and angle strain. What we have here, these things being eclipsed to each other, is torsional strain. What is that? Like this, it's this hydrogenous thing. Like it's clear if I put both these groups both up. Now they're like really eclipsed. Now it's like no one's going to argue with me about this being eclipsed. Torsional strain, torsional strain is this stuff where these things are kind of banging into each other. You have this eclipsing effect. This is substituent driven. There is a little bit of angle strain in a 5-membered ring, but it's hard to see, so I'm not going to try it. What I'm going to do is I'm going to take us down to a 3-membered ring, and you're going to see what angle strain is. Unplug all those. Now I'm trying to make a 3-membered ring, and I can't, right? Like, look at what I'm doing to my poor bond up here. I'm trying to break my model kit, trying to make this 3-membered ring. This is angle strain. My model kit is SP3. It wants 109.5 degrees, and I'm trying to make it 60 degrees, and it does not want to do 60 degrees because that angle is not stable. It doesn't want to do 60. It wants to be 109.5. That is angle strain. Breaking your model kit. To make a 3-membered ring. Is angle strain. It's about the angle of the substituents. Yeah, no, exactly. Oh, shit. Yes, there's nothing much interesting on my screen. I will share my screen. No, I think we're good. I think I've displayed this with my video. So eclipsing is torsional strain. Breaking your model kit is angle strain. Yeah, and the 3-membered ring has massive torsional strain because everything's eclipsing everything in a 3-membered ring. If you want to go back to the lecture notes that I have in the lecture. I did a lot better with the pre-prepared drawings. You don't need to know. You need to know. You're not going to need to draw any envelopes in 3D. You're going to need to draw chairs. So you're going to be asked questions about 5-membered rings, but they're not going to be draw the different conformations of this because there's actually 5 different envelopes for each 5-membered ring. Whereas there are only ever 2 chairs. So we're going to keep it simple, stupid. And not that you're stupid. We're going to keep it to 6-membered rings only. There's only 2 chairs to keep track of. Okay. So in this case, these 2 would be trans, and they're just kind of one kind of up. And one kind of down. And they're neither axial nor equatorial because screw you, it doesn't make sense. 5-membered rings. Suck for drawing. They're actually pretty stable things, all told, but they suck for drawing. Yeah, I can read what I wrote. That's a very good question. The top line says eclipsing is torsional strain, substituent driven. So it's all about the substituents eclipsing each other or not eclipsing each other. That's what torsional strain is. Are the substituents eclipsed, gauche, staggered? That's all torsional. Breaking your model kit to try and make a 3-membered ring, that's angle strain. Angle strain is about the angle of the ring, the atoms in a ring not wanting to make that angle. Both of those cost energy. One, torsional strain because electron clouds are banging into each other because they're eclipsed. Angle strain because the bonds want to be a specific angle and you're needing to twist them out of the preferred orientation. Okay, let's do one last example. I'm going to go back to the 6-membered ring. And this will lead into next class where we do some more examples of this because this stuff is hard. It is, like you're not crazy or anything if you're finding this really difficult. It is really difficult. Okay. So we have this guy. Draw a chair. And if you draw one chair, draw the other chair. It's a nice day out there. Okay. So I'm going to draw 2 chairs, and I'm going to do this kind of in parallel. You'll have drawn one of these or the other one. So either 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. And I'm going to arbitrarily do 1, 2, 3, 4, 5, 6. So you must go, if you go clockwise on one, you're going clockwise on all of them. Just keep going clockwise. If you like numbering counterclockwise, that's cool too. Then just always go counterclockwise. Okay. So carbon 1, back here, I can sketch in the hydrogen if it helps me. There's a down position and an up position. And I'm going to pretend that the bond continues down below that, like I'm showing that it's going behind because, you know, it's broken. The hydrogen is in the down, the ethyl group is in the up. Then on carbon 3, the OH is in the up, and the fluoride is in the down. That's one of the chairs. The other chair you might have drawn is you went, okay, well, it's axial for the ethyl group and equatorial for the hydrogen, and axial for the OH, and equatorial for the fluoride. Either one, those are both the chairs. So on your chair, if the OH is up, the ethyl group is up, and they should both be equatorial or both be axial. If you have a one where your ethyl group is axial and your OH is equatorial, you've done it wrong. So these are the two chairs. And now the question is, which one of these is more stable? You do not have to include the H, Lou Jane. You never need to include the H. You can if it helps you. But H's are always implied. Brendan saying the first one's more stable. Nora saying the second one is more stable. We're at a 1-1 tie. Okay, the votes are coming in. Perfect. We're overwhelmingly coming around to the first. And so hopefully what you're thinking is, I got 2 equatorial substituents in the first one and 1 axial, and I've got 2 axial substituents in the second one and 1 equatorial. So on pure numbers, I like the first one. Then at the beginning of this lecture, in a chat window, I shared a link to Wikipedia A-value table. We're going to talk about A-values next class in reference to all this stuff. But if you look at the A-values, you'd find and interpret them. And if you read the Wikipedia article, it's actually really quite good. I've edited it in the past, so I think all my edits have been lost because the Wikipedia editors are special. Fluoride is about as small as you can. It's the next best thing after hydrogen and deuterium. It's the smallest atom. It takes the least amount of space. So having a fluoride equatorial or having a fluoride axial is not that bad. But having an ethyl group or an OH axial is kind of sucky. And so much more stable. Two bigger things are equatorial. So it's not just more equatorial, more and bigger are equatorial. And we can actually play a game, it's not a very fun game, but we can play a game with the A values where you can actually add them up to get the answer over what's going to be equatorial and what's going to be axial. So good, everyone who came in with first, you're absolutely right. So one of the take-home assignment, one of the assignments I assigned, one of my own stuff, has a lot of practice questions trying to draw chairs, draw lots of chairs. Good practice. I like rings. I like resonance and rings. So mostly because nature likes resonance and rings. So you end up drawing a lot of them. And nature loves six-membered rings because there's no torsional or angle strain on a six-membered ring. Everything is perfectly staggered in a chair, and all the bond angles are 109.5 degrees. So everything is perfect in a chair. A chair, like a six-membered ring chair, is a perfect structure. It underlies diamond after all. 2 slides. Yes, I certainly can. So Lauren asked in that final example, is that an example of trans or cis? It is neither. The OH and the ethyl group, if you have them drawn in front of you, are cis to each other. The ethyl group is trans to the fluoride. And the fluoride and OH are neither cis nor trans to each other because they're on the same carbon. So that molecule is neither cis nor trans, but specific substituents are cis or trans to each other. Do you have any question about this, Drake, or you just wanted to see it again? I'll be uploading this afternoon, I hope. Okay. So yeah, so what do I mean by that, Lauren? I can't say whether this molecule is neither cis nor trans. You can't call it cis or trans. Once you have more than 2 substituents, 2 non-hydrogen things, it's neither cis nor trans. Just individual substituents are cis or trans to each other. Yeah. Okay. I am seeing no more questions, so I'm going to hand this over to my colleague, Samra, who can then take it from here. Are the 2 methyls on the isopropyl axial equatorial? So Christian, it only applies to what's directly attached to the ring. The isopropyl, we don't talk, like here, this ethyl, we wouldn't talk about this being axial equatorial. This whole group is axial equatorial, but this particular thing doesn't matter. We're not talking about this. It's got free rotation, it spins around like a top. Okay, Samra, over to you. I think I'm going to stop recording, so you can start recording if you want to record your thing.